In this lesson, we are going to talk about a really cool trick that we can use to evaluate limits known as Hopital's rule. And we needed to previously get really comfortable with taking derivatives because when we use Hopital's rule, we are going to be taking the derivative. So with this rule, we can evaluate limits that we haven't been able to evaluate yet using the tools that we have other than maybe making a table. And when you make a table, you're really just trying to make your best guess at what the limit is and your best approximation. But with Hopital's rule, you can actually find the exact value. Before we get into Hopital's rule, though, we have to talk about what's called indeterminate forms. So in calculus, an indeterminate form is an algebraic expression where you have two different functions that are combined together, and you cannot find the limit based solely on using the limit laws and breaking up those functions and taking the limits individually. And so what happens is you get an expression that is hard to evaluate. And these are called indeterminate forms. So we have 7 of them. So when you try to take the limit of functions that are combined and use the limit laws to separate them, if you get any one of these 7 expressions here, this is what's called an indeterminate form. It is because these do not have any numerical value that we can identify. So typically when we say 0 in the numerator of a fraction over anything else would be 0, like 0 over 7, 0 over 5. Those would all give me 0. And then we also have that rule that says, well, if there's 0 in the denominator, it's undefined. So now we have this conflict. Well, is it 0 or is it undefined? So it's where we have these conflicts and it's hard to determine what the value is. So there's one of our indeterminate forms. We also have infinity over infinity. And a lot of people will say, well, why isn't that just 1? You know, when we have a fraction that has the same thing on the top and the bottom, it's just 1. Believe it or not, there are different sizes of infinity. And another thing to consider is that infinity isn't an actual value. So this is also hard to determine. And the same reason for this one, right? And infinity is not a value that we can calculate. Now, the two rules that are conflicting here are the rules that, well, if I have some constant raised to the power of 0, that's going to be 1, right? 7 to the 0 is 1. 5 to the 0 is 1. And then we also have the conflicting rule where if I have 0 to some power, it's going to be 0. So the question is, does this represent 1 or does it represent 0? This one here was is this 0 or is it undefined? These two here are big question marks because infinity isn't a value that we can calculate. Now I'm making the same argument for all of these. Infinity is not a number, so we can't treat it like a number. Now you can use Hopital's rule when you have 2 possible cases for indeterminate forms. If you take the limit as x approaches some value of a, and you have some ratio of 2 different functions, f of x over g of x, and you get the form 0 over 0 or infinity over infinity, with these 2 forms here that are indeterminate, you can use what's called Hopital's rule. And Hopital's rule says you can take the derivative of f and divide it by the derivative of g and then take the limit. So here's Hopital's rule. Let me write it down for you. This only works if you have the case 0 over 0 or infinity over infinity. If it's any other indeterminate form, this will not work. The limit as x approaches a of f of x over g of x, you can say that that's equal to the limit as x approaches a of the derivative of f over the derivative of g. And you can repeat that as many times as you need to check to see if you can take the limit, as long as you keep getting indeterminate forms that are 0 over 0 or infinity over infinity. So let's walk through the first example, and I have parts A through D here, and these are all cases when you get 0 over 0. If I take the limit as x approaches 0, and if I try the limit laws in direct substitution, I'm going to get 0 over 0. Because if I plug in 0 for cosine, cosine is 1, and then I have 1 minus 1 on top, which is 0. And then, of course, if I plug in 0 in the denominator, I'll have 0. So the limit as x approaches 0 of 1 minus cosine x over x gives us the indeterminate form of 0 over 0. Now, because we have 0 over 0, it's one of the two cases that we can use Hopital's rule. So I can say that the limit as x approaches 0 of 1 minus cosine x over x is equal to the limit as x approaches 0 of the derivative in terms of x of 1 minus cosine x over the derivative with respect to x of x. So now I take the derivative. I take the derivative of 1, that's 0. When I take the derivative of minus cosine x, I'm going to get a double negative because the derivative of cosine x is negative sine x. And then with that minus in front, I'm going to get a positive because of that double negative. So on top, I'm going to have sine x. On the bottom, when I take the derivative of x with respect to x, x just 1. So now I can try to take the limit as x approaches 0 of sine x instead, and it's going to be equivalent to taking the limit as x goes to 0 of 1 minus cosine x over x. Now, when I try direct substitution now, and I plug in 0 for sine x, I'm going to get 0. Okay, part B, we're going to find the limit as x approaches 1 of sine pi x over the natural log of x. When I try direct substitution and limit laws, and I plug that one in, if I take the sine of pi in the numerator, that gives me 0. And when I take the natural log of 1, that also gives me 0. So I'm dealing with the indeterminate form of 0 over 0, which means I can use Hopital's rule. So I'm going to take the limit as x approaches 1. I'm going to take the derivative with respect to x of sine of pi x over the derivative with respect to x of the natural log of x. Now, when I take the derivative of sine pi x, the derivative of sine is cosine, but because I have that inner function of pi x, I now have to use the chain rule and multiply by the derivative of pi x, which is pi. So I'm going to have pi times cosine of pi x. That's going to be my derivative in the numerator. Now, when I take the derivative of the natural log of x, I'm going to get 1 over x. Now, let's try direct substitution and limit laws now. So when I plug in 1 for x in the numerator, I get cosine of pi, which is -1. And then I have -1 times pi, which is negative pi. So on top, I have negative pi. On the bottom, I have 1 over 1, which is just 1. So my limit as x approaches 1 of sine of pi x over the natural log of x is just negative pi. Okay, let's look at example C. The limit as x approaches positive infinity of the function e to the 1 over x minus 1, all divided by 1 over x. Now, as I plug in really large numbers in the positive direction, that exponent, 1 over x, for the natural exponential function, that's going to get smaller and smaller and smaller till that limit is 0. So now I'm going to have 0 in the exponent. So I have e to the 0 minus 1 all over. And then 1 over x, as I plug in really, really, really large numbers, that's going to approach 0. E to the 0 is 1. So in the numerator, I get 1 minus 1. And that will give me 0 over 0, which we can use for L'Hopital. So I'm going to say that the limit as x approaches infinity of e to the 1 over x minus 1 all over 1 over x is the same as taking the limit as x approaches to infinity. If I take the derivative of the numerator with respect to x all over the derivative of the denominator with respect to x. I'm going to copy down the limit as x goes to infinity. Now if I take the derivative of e to the 1 over x, I use the rule for the natural exponential function, and what I would get is e to the 1 over x. So I use the same function, but then I have to multiply it by the derivative of the exponent. And the derivative of the exponent is going to be negative 1 over x squared. You can use the quotient rule for that, or you can rewrite 1 over x as x to the negative 1 power and then use the power rule. Either way, you're going to get the same thing. So this is the derivative for e to the 1 over x. And then when I take the derivative of the minus 1, that's a constant, so that's 0 and it disappears. Now in the denominator, if I take the derivative of 1 over x, I'm going to get negative 1 over x squared. Again, you can use the quotient rule, or you can rewrite 1 over x as x to the negative 1 and use the power rule. So now I can cross this off and I cross this off, and I get the limit as x goes to infinity of e to the 1 over x. As we plug in really, really, really large numbers for that x in the denominator, the whole fraction goes to 0. So we end up getting e to the 0, which is 1. Okay, part D. As x goes to 0, I'm going to get 0 minus 0 in the numerator, and then obviously when I square 0, I'm going to get 0 in the denominator. So I have that indeterminate form of 0 over 0 again, which means L'Hopital's rule will apply. So I can take the limit as x goes to 0 of sine x minus x over x squared, and set that equal to the limit as x goes to 0 of the derivative of the top and the bottom separately. So I'm going to take the derivative of sine x minus x with respect to x, and then I'm going to take the derivative of x squared with respect to x. Now when I take the derivative of sine x, I'm going to get cosine x. When I take the derivative of that minus x, that's going to give me a minus 1. When I take the derivative of x squared, that's going to give me 2x. So now when I plug in 0 and try the limit laws and direct substitution again, we get, if you notice, again, 0 over 0. The cosine of 0 is 1, and I get 1 minus 1 on the top. And then I get 0 in the denominator. So this is a case where I can use L'Hopital's rule a second time because I still have that indeterminate form. So I'm going to take the derivative again. I'm going to say, well, this is equivalent to the limit as x approaches 0, and now take the derivative of the top again. When I take the derivative of cosine x, that gives me a minus sine x. When I take the derivative of minus 1, that's a constant, so it disappears. And then when I take the derivative of 2x, I get 2. Now when I plug in and try direct substitution and limit laws here, I plug in 0 and I get 0 over 2, which is 0. So this is a really good example of where you can use L'Hopital's rule more than once. You just have to make sure that you can apply it a second time by making sure that you're getting one of those two indeterminate forms. In the next couple of examples, we're going to go through the same idea, but we're going to show you the case where you can get infinity over infinity. So in this first example A, it says the limit as x approaches infinity of 3x plus 5 over 2x plus 1. Now certainly if you start plugging in really huge numbers, the top is going to grow without bound and the bottom is going to grow without bound as well. So this is where you have the case of infinity over infinity. So because we have that indeterminate form, we can apply L'Hopital's rule. So I can say that the limit as x approaches infinity of 3x plus 5 over 2x plus 1 is equal to the limit as x approaches infinity of the derivative with respect to x of 3x plus 5 over the derivative with respect to x of 2x plus 1. Now, when I take the derivative of 3x plus 5, that's going to give me a 3. And when I take the derivative of 2x plus 1, I'm going to get 2. Since this is just a constant function, it's a horizontal line at 3/2, the limit is going to be 3/2. Now, if you think back to, I can't remember what section it was, but we talked about doing this example without using L'Hopital's rule. So if you recall, the other way that we did it before we learned L'Hopital's rule, as we would look for the largest exponent for x and divide everything by that term. So in this case, I would divide everything by x. So when I divide 3x by x, I get 3. When I divide 5 by x, I get 5 over x. When I divide 2x by x, I get 2. And then when I divide 1 by x, I get 1 over x. And then as I start plugging in numbers that are really, really big, the denominators get so big that the whole fraction approaches 0. And then we're left with 3/2. And then we also talked about this in college algebra when the degree of the numerator is the same as the degree of the denominator. When we're looking at a rational function, we can just take the leading coefficients and divide them, and that will be our end behavior where our value of y is flattening out. And that's exactly why, because we're taking the derivative of the top and the bottom, and what we're going to be left with is those leading coefficients. Okay, the next example in part B, we have the limit as x approaches 0 from the right of the natural log of x over cotangent of x. Now, if you think back to the graphs of the natural log of x, it looks something like this. And when you think back to cotangent graphs, you have asymptotes that look like this. And the graph of cotangent looks like this, and it repeats. So we are going to get that indeterminate form. On the top, we're going to actually have negative infinity, because if you look at the graph of the natural log of x and you trace it approaching 0 coming from the right, it's going to be negative infinity. Now coming from the right, looking at cotangent, it's going to go to positive infinity. So we have that indeterminate form, and we can apply L'Hopital's rule. So I'm going to say that the limit as x approaches 0 from the right of the natural log of x over cotangent of x is equal to the limit as x approaches 0 from the right of the derivative with respect to x of the natural log of x over the derivative with respect to x of cotangent x. Now, as I take the derivative of the natural log of x, I'm going to get 1 over x. When I take the derivative of cotangent of x, I'm going to get negative cosecant squared x. I can simplify this a bit by writing, let's see, 1 over x cosecant squared x, and then throw this negative in front. I just took negative cosecant squared x over 1, and when you divide a fraction by a fraction, you flip and multiply, so we end up with 1 over negative x cosecant squared x. If I try to use direct substitution here, we're going to run into a problem because as x approaches 0, and I plug in to x, that's going to give me 0, and when I plug in 0 for cosecant approaching from the right, that's going to give me infinity. So we can't really determine anything yet, and we're going to see if we can do a little bit more algebraic manipulation here. Now, I can't use L'Hopital's here again because I don't have that indeterminate form of 0 over 0 or infinity over infinity. So I have to try to find a different way to approach this. And so what I'm thinking is, since cosecant and sine are reciprocals, I'm going to rewrite this. Instead of having cosecant squared in the denominator, I'm going to write it as sine squared in the numerator. So now if I approach 0 from the right of sine squared, I'm going to get 0. And then for negative x, that's going to give me 0. So I'm now in the form that I can try to use L'Hopital's rule again because I get 0 over 0. So I can say that that's equal to the limit as x approaches 0 from the right. And now I'm just going to take the derivative of the top and the bottom. So I'm going to have to use the chain rule with sine squared. So I bring the 2 down in front. I decrease my exponent by 1, and then I have to take the derivative of the inside, which is cosine x. And then when I take the derivative of negative x on the bottom, that gives me negative 1. Now when I try direct substitution, I'm going to get 0 in the numerator and negative 1 in the denominator. So 0 over negative 1 is 0. So we can say that the limit as x approaches 0 from the right of the natural log of x over cotangent of x is 0. And it doesn't hurt, especially when you have a complicated problem like this, to actually plug that function in on your calculator and verify that as you're approaching this function from the right, you're getting closer and closer to 0. So the last few examples we have to go over, I'm going to show you some other indeterminate forms that we cannot use L'Hopital's rule for. So I can't stress this enough. In order to use L'Hopital's rule, you have to have one of the two indeterminate forms of 0 over 0 or infinity over infinity. If you do not have that, L'Hopital's rule will not work. But when you run into other indeterminate forms, there are tricks on how to handle it. So in this first example, we're going to get that indeterminate form of getting 0 times infinity. If we use direct substitution here, if I plug in 0 for x, I'm going to get 0. And if I plug in 0 for the natural log of x, as we approach the value of 0 coming from the right on that graph, it's going to negative infinity. So we have the case here where we have the indeterminate form of 0 times infinity. So one of the tricks that you can use is you can try to rewrite this algebraic expression and use the tools that you learned in college algebra on how to manipulate expressions in order to rewrite it in a form that we can use L'Hopital's rule. So here's one trick. If I rewrite this, instead of leaving it as x natural log of x, I'm going to rewrite this as natural log of x over 1 over x. This expression and this expression are equivalent algebraically because if I simplify that complex fraction by flipping and multiplying the 1 over x, I'm going to get x natural log of x. So all I did was I rewrote it in a way that now we can use L'Hopital's rule. So now I'm going to have the indeterminate form of minus infinity over infinity. So now I can use L'Hopital's rule. So I can say that the limit as x approaches 0 from the right of the natural log of x over 1 over x is equivalent to the limit as x approaches 0 from the right of the derivative with respect to x, natural log x, over the derivative with respect to x of 1 over x. Now, when I take the derivative of the natural log of x, I'm going to get 1 over x. And then when I take the derivative of 1 over x, I'm going to get negative 1 over x squared. Now, when I simplify that, I'm going to get negative x. And now I can use direct substitution and see that I get 0. So just by using this trick to rewrite this expression, I turned it into a way that I can use L'Hopital. Here's another indeterminate form, infinity minus infinity. So we're going to start off by trying to combine these fractions. So I'm going to find a common denominator, which will be x squared tangent x. So when I create a common denominator and I combine those fractions, I'm going to get tangent x minus x squared all over x squared tangent x. Now, as x approaches 0 from the right, the numerator is going to approach 0. And the denominator is going to approach 0. So now I have the indeterminate form 0 over 0, and I can now apply L'Hopital's rule. So I can say that the limit as x approaches 0 from the right of tangent x minus x squared all over x squared tangent x is equivalent to the limit as x approaches 0 from the right of the derivative with respect to x, tangent x minus x squared, all over the derivative with respect to x of x squared tan x. So now let's take the derivative. If I take the derivative of tan x, that gives me secant squared x. And when I take the derivative of minus x squared, I'm going to get minus 2x. When I take the derivative of the denominator, I'm going to have to use the product rule because I have two functions. I have x squared and I have tan x. When I use the product rule, I should get x squared secant squared x plus 2x tan x. Now, as I try to see what happens as x approaches 0 from the right, secant squared x minus 2x is going to approach 1. And then the denominator, x squared secant squared x plus 2x tan x, that's going to approach 0. So this is going to blow up as that number in the denominator gets smaller and smaller and smaller. The whole fraction gets bigger and bigger and bigger, and this is going to blow up, and I'm going to get infinity. So this limit as x approaches 0 from the right of 1 over x squared minus 1 over tan x has to be infinity. And you can verify that by looking at the graph. Now here's an indeterminate form that is infinity to 0. So let's evaluate the limit as x approaches infinity of x to the power of 1 over x. So because I see that this is kind of a weird function, I have x to the power of 1x, and typically when I have strange exponents like this, it makes me want to take the natural logarithm and try to manipulate that so that the exponent can come down in front. So I'm going to use a substitution trick here, where I'm going to say let m be x to the 1 over x. So then I'm going to take the natural log of both sides. So I have the natural log of m is equal to, now I can bring that exponent down in front, 1 over x, natural log of x. And then I can rewrite that as the natural log of x over x. So now if we evaluate the limit as x approaches infinity of the natural log of m, we would get the limit as x approaches infinity of the natural log of x over x. And now we can apply L'Hopital's rule because we have a situation where we have infinity over infinity. So I can say the limit as x approaches infinity of the natural log of x over x is equal to the limit as x approaches infinity of the derivative with respect to x of natural log x over the derivative of x with respect to x. So when I take the derivative of the natural log of x, I'm going to get 1 over x. And then when I take the derivative of x, I get 1. So when I think about plugging in really, really large numbers at this point, I'm going to get 0 over 1, which is 0. So what this tells me is that this is what we have so far, that the limit as x approaches infinity of the natural log of m, that was my substitution, we got 0. Since the natural log function is continuous, we can use the limit laws to say, we can switch this around and say, well, I can just take the log of the limit as x approaches infinity of m, and that should be 0, which means this would have to be equal to 1. If I take the natural log of 1 and get 0, then whatever is inside there has to be equivalent to 1. So then we can say the limit as x approaches infinity of m has to be 1. And what did we substitute as m? If we come back up here and remember, m was that weird function, x to the 1 over x. So we can say that the limit as x approaches infinity of x to the power of 1 over x is equal to 1. And this is what we were trying to find out from the beginning. Okay, last example for indeterminate forms. We're going to do an example of getting into the situation. We have 0 to the 0. So when we look at this limit, the limit as x approaches 0 from the right, we have x to the power of sine x. When I try to use direct substitution, we run into the problem of having 0 to the 0. We're going to try that substitution trick again, where we let m be equal to x to the power of sine x. And then we're going to take the log of both sides. And then we can bring that sine x down in front. And now we're going to try to evaluate the limit as x approaches 0 from the right of sine x natural log of x. Now, when we try to evaluate this, what's going to end up happening, we're going to get another indeterminate form of 0 times infinity. So that's not going to work. So let's try rewriting this in a way that we can use L'Hopital's rule. Let's try the limit as x approaches 0 from the right. We're going to have sine x, and I'm going to write the natural log of x in the denominator as 1 over the natural log of x. Now I get the indeterminate form of 0 over 0, because if I start plugging in points that are close to 0, for sine x, I'm going to approach 0. And then for natural log of x, those numbers are going to get really, really big. And since that's in the denominator of fraction, the whole fraction is going to get really, really small. So the denominator is going to approach 0. So now I'm going to try to take the derivative and use L'Hopital's rule. So I can take the limit as x approaches 0 from the right, and I can use L'Hopital's rule by taking the derivative of sine, which is cosine x, and then take the derivative of 1 over the natural log of x. You can either use the quotient rule or try to rewrite it in some way to use the power rule. But either way, in the denominator, you're going to get negative 1 over x times the natural log x squared. Now I can rewrite that. Let's see if we can get rid of this complex fraction. If I do a flip and multiply, I'm going to get cosine times negative x natural log of x squared. And unfortunately, that doesn't look like that helps us again. So this looks like it's going to leave us with another indeterminate form that we cannot use L'Hopital's for. We're going to end up getting 0 times infinity, because this will give us negative infinity. And then when I plug in 0 here, that's going to give me 0. So we have another indeterminate form. So we got to figure something else out. So back up here, we tried rewriting sine x times the natural log of x as sine x over 1 over natural log of x. Let's try rewriting it a different way now, since this way didn't work. So let's cross this off. This didn't work. So we had before sine x natural log of x, and then we tried to do a trick with the log where we divided by the reciprocal. Let's try to use that trick now with sine. See if that gets us anywhere. So I'm going to leave the natural log of x in the numerator, and I'm going to divide by the reciprocal of sine. And then we can rewrite that. If we don't want it to be too messy, we can rewrite that as the limit as x approaches 0 from the right of the natural log of x over, and then use cosecant x, because cosecant x and sine are reciprocals. Now, when we try to use direct substitution, we'll get negative infinity over infinity again, and we can try using L'Hopital. So we're going to take the derivative of the natural log of x in the numerator and get 1 over x. And then we're going to take the derivative of cosecant x, and in the denominator, I'll have negative cosecant x times cotangent x. We can try to rearrange this to make it a little less complicated by using our trig identities. I know that secant is the reciprocal of sine, and I know that cotangent is cosine over sine. So a little scratch work off here down to the side. If I have minus cosecant, which is 1 over sine x, and then I have cotangent, which is cosine x over sine x, I can rewrite that as negative cosine x over sine squared x. All of this in the denominator is minus cosine x over sine squared x. And then when I flip and multiply, I'm going to get 1 over x times sine squared x over cosine x. Now I can rewrite this again as the limit as x approaches 0 from the right of sine over x times sine x over cosine x by splitting up those two signs. And that gives me the limit as x approaches 0 from the right of sine x over x times tangent x. Now, these are limits that we know. After doing some manipulation with these trig identities, we know what the limit as x is approaching 0 from the right of sine x over x. We studied that before. That's 1. And then when we take the limit as x approaches 0 from the right of tangent x, that's 0. So we end up with 1 times 0, which is 0. So what this tells us is we have that the limit as x approaches 0 from the right of the natural log of our substitution m, we found that that was 0. Because the natural log is continuous, we can take the log of the limit And so we can rewrite it like this using our limit laws. And again, this is because the natural log is a continuous function. And our substitution for m was x to the power of sine x. And when we substitute that back in, if we know that the natural log of this limit is 0, then whatever this is inside here has to be equal to 1. And that was the limit that we were trying to find. The limit, as x approaches 0 from the right, of x to the sine x is equal to 1. Very long, very painful, but it works. So what it comes down to is the two big points that I want to emphasize is if you use Hopital, it has to be in the form of 0 over 0 or infinity over infinity for those indeterminate forms. If it's another indeterminate form, you need to use some kind of substitution or algebraic manipulation in order to get it in a form that you can use Hopital or that you can solve it directly using the previous rules that we used, like the limit laws and things like that.